I'm hitting the record button and let's go. This is day number 2. We will discuss IOI 2014 day 2. Just before that, please put your scores in the spreadsheet. The link is in the announcements. And also in the announcements you will find a link to Shkopu contest. This is the platform where we will do Polish Olympiad days. Those will be tasks from a year ago or so, translated to English. If the platform doesn't work for you, then I will also then provide some alternative links or just PDF with statements. For your convenience, I set up the contest so it would start tomorrow and last for around 24 hours, even more than that. So just anytime you want, you can do your participation, but limit yourself to 5 hours. But for your convenience, you can participate tomorrow, which is Monday, or on Tuesday morning, and we will discuss on Tuesday afternoon, same time as today, just 2 days from now. So go register there. In case there are some issues with registration, it's better if we are able to resolve it today instead of tomorrow. Maybe I will not be online and you want to do something. You want to start your virtual participation. Let's look at IOI 2014 results and medals. Again, just like we talked about yesterday, those results wouldn't be very up to date, that much up to date, because nowadays people are stronger. So here gold cutoff was 449 points, and let's say today it would be 480 points maybe for gold. I'm just guessing. Then silver is the total of 320 points. Let's say now it would be 360. And bronze is 220 points. Now let's say 250. Just I'm guessing. The biggest difference, I would say, especially for around silver and bronze, is the problem wall, where nowadays I would expect many people to solve it. Other problems are not that much different. Right. Maybe the problem... which problem is that? Not friend. Holiday. Holiday is also something that I would expect people to be better at nowadays, but we'll see. So congrats to those who got medals here. And now let's start discussing problems. Why my tablet doesn't work? Come on. I want to draw. Well, I will try to replug it a few times. For now, no drawings. Okay, first task, gondola. What do we have here? We start with a series of numbers 1, 2, 3, 4, 5. It might be rotated. So maybe we start with something like 3, 4, 5, 1, 2. But the order is this, just shift it. And then one by one, they are being replaced by bigger numbers. So something is replaced with a 6, then something is replaced with a 7, something is replaced with 8, with 9, and so on. There are several parts of this problem, and part 1 is one just to decide, check if possible. So check if the final sequence given to you is possible or not. Return yes or no. Is that correct? Yes. We need to check if it's valid. So check if valid. Part 2 is find possible order of operations to make it valid, to obtain such a sequence from the initial one. And part 3 is count possible operations, count sequences of operations. This is finding one example order of operations. This is counting all possible sequences, valid sequences of operations. We will discuss those 3 parts. We will not dive into smaller subtasks here, because I think it's enough to break it down into such parts. So first, check if something is valid. Something is obviously not valid if there are equal numbers anywhere. So to check if it's valid, it needs to be all distinct. And second condition is that if there are some original values there, they need to be in good order with respect to each other. For example, it's not possible that there is 1 and 5. If n is equal to 5, then this sequence shifted as 1, 2, 3, 4, 5. If there is 1 here, then 2 must be here. Any numbers that are up to n must be in valid respective order. For example, if there is a 2 here, and there is 4 somewhere, 4 must be here. So look at all numbers that are from 1 to n and check their respective distances. One way to do it is the following. Find any one such a number. So let's say we find position I, any one position where there is number that is up to n. For every other number j, or for every other index j, such that it's also a of j is up to n, so it's a number from 1 to 5 in this case, we check if the distance of values is equal to the distance of indices modulo n. How can we do it here? We would like to avoid different cases where what if j is here. So what do we want to do? I think we can compute the difference as j minus I. If this is negative, then increase it by n. If diff smaller than 0, then diff plus equal n. This will compute the distance. Let's see, here it would be -2 plus 5, it's a 3. 1, 2, 3, yeah. And you do the same with values. d2 is equal to aj minus ai. If d2 is smaller than 0, then d2 plus equal n. And now those two values should be equal to each other. That's one possible check. If d2 and diff are equal, it means that, yeah, it's the same distance. For 2, 3 units later, there should be 5. Alternatively, once you see 2, you check if the next number is 3 or it's bigger than n. You check if the next number is 4 or bigger than n, and so on. Every number, you have one candidate for what it can be. So also you can from here start a for loop and one by one check, increasing the value that should be there by 1. After 5, of course, there should be 1. So you can like that iterate. If no number is here between 1 and n, then this is okay. You don't need to do anything. So this, and check relative positions of values 1 in 1 to n. Find any one of them and compare with others. Then, part 2, find the order of operations. I find it easiest to just, let's take this. I find it easiest to just say that all numbers bigger than 5, they were temporarily here. So I find the biggest number because this is the one that maybe was replaced most times, and I say this is the number, this is the position where everything was. So we look at this thing. we find again any number that is up to n, like this one, and it implies what is the starting sequence. In this case, the starting sequence needs to be this. So we say, okay, this is what was there at the beginning. If there is no single number that is up to n, then we choose any starting sequence. It can be from 1 to 5, just like this. But here, there was at least one number up to 5. And now, we know that here should be 8, here should be 10 at the end. So I say here, this will be replaced with 8, this with 10. But there are some other values that temporarily should be here. There should be a 6, and there should be 7 and 9. 6, 7, 9 are missing. This is the input sequence, this is the starting sequence apparently. So I'm going to put 6, 7, 9 just before a 10. So this 3 I'm going to change into 6, then into 7, then into 9, then into 10. 1 can change to 8 at any point, it doesn't matter the order, so maybe this is the first operation. So, solution to part 2 is find any number that is up to 5, up to n. It decides what should be the starting sequence. I mean, you do this anyway because of that. Because you first can check if something is valid, also you check if there are distinct values. Then all the values that in this input sequence are bigger than n, like 8 and 10, we should obtain them. But before we do that, we can collect all numbers that are greater than n, but smaller than the maximum. So in this case, you can iterate numbers from 6 up to 9. For each of them, if it's not present in the input, for that you can have a set or Boolean array. If it's not present in the input, temporarily put it on the position of the final maximum. So here we find the maximum and we say 6 goes here because 6 is greater than n and it's not there yet. 7 goes there, then 8 doesn't go there because 8 needs to go somewhere else. So I don't know, at that point we can put 8 here. Then 9 goes here, and finally 10 goes here. Find the position of maximum, and all the values that do not exist in the input, you put there for a moment. Eventually it will be anyway replaced with maximum. That was part 2. And finally, part 3 of Gondola is that sometimes here we have a choice of what to do. In this case, values 6 and 7, they don't need to go to this position to be replaced by 10, but also they can go here. They can go to the position of where eventually 8 is. Also 7 can go here instead of there. And 9 needs to go here before 10 because only 10 is a greater number that can replace it. We cannot put 9 here because 9 only can be, any number can be only replaced by bigger numbers. So, a number and not existing in the input can go at any position where eventually there is a greater number. And this eventually just means where in the input there is a greater number, because this is the final sequence that we want to obtain. Right, so we just need to count such positions. I will show a slightly bigger example, or more interesting example maybe. Let's say 5, 8, 2, 10, and 14. I know that initially it's 1, 2, 3, 4, and a 5. There are some numbers that are missing. I actually cannot iterate them for the full score because numbers can be up to billion. But there are numbers 6, 7, 9, 11, 12, 13. Those values are missing. I need to put them somewhere. Value 6 can go to any of those 3 positions. Value 7 also can go to any of those 3 positions, because each of those can be replaced then by something greater. Then we put an 8 here for sure, and then 9 can go only to those 2 slots. 11 and 12 and 13 only can go here. So for number 6, we had 3 possibilities of where it goes. For number 7, also 3 possibilities. That's 3 times 3. Then number 9 can go to 2 positions. Then number 11 can go only at this position, 12 here, 13 here. So there are 18 ways how we can obtain this sequence. For every number that is not here, well, if it's up to n, then we figure out where it should be, with one exception. If it's greater than n, so 6, 7, and so on, there are some positions where it can go. So a brute force first is that answer is 1 for every value, some kind of x, from n plus 1 all the way up to the maximum minus 1. For every such number, if this doesn't exist in the input, if x not in the input, which you can check with a set or some kind of sorting, then answer times equal greater values. Greater values is in the input how many numbers are greater than me, which you can do linearly for quite bad time complexity. You can also do it with binary search. But we will in a moment get rid of even this for. The sequence of values that are missing can be decided by looking at values that are present here if we sort them. We have values, of course, from 1 to n, in this case from 1 to 5, then 8, 10, and 14. Between every 2 consecutive values here, there are missing values. Here is 6 and 7, here is 9, here is 11, 12, 13. And every such block behaves in a way dependent on the number of your greater elements. For each of 6, 7, they can go to one of 3 slots, those positions of greater numbers. So we multiply the answer by 3, sorry, this one by 2, and so on. Let's use a bigger example. Let's say here it's 50, then it's 200, then it's 1000. Then I know that here all the values from 6 to 49, and the number of such values is what, 44? There are 44 values here. Each of them has 3 slots where it can go. So, and now it would be very nice to draw. We have 3 possibilities to the power of 44. 44 here is the number of elements that are in between of 5 and 50. Multiplied by, then between 50 and 200 there are 149 elements. That's 200 minus 50 minus 1. There are here 149 elements that are not in the input, but we need to put them there temporarily. Each of them has 2 possible slots. So actually I should say that this is 2 at power 149. And then times 1 at some power doesn't really matter. We can ignore that. And that's the answer. In the last subtask, the values are up to 1 billion, so those exponents are up to 1 billion as well, which is why you need to use binary exponentiation. Is this the spelling? Yes. You use binary exponentiation modulo 1,000,000,009. So you sort first the values, the big values from the input, including for convenience the number n. Between every 2 numbers here, you know how many there are and how many remaining greater values there are in this sorted sequence, and you multiply the answer by such power. There is one more thing that we need to use. Also, first, there can be contradiction. So always we first check if the sequence is valid. So we just run our check from part 1. If the check fails, then we return 0, we print 0. And one more thing is that the special case, there might be no values up to n. So maybe the sequence just looks like this. If the sequence looks like this, for n equal 5, then you don't know where are values 1, 2, 3, 4, 5. There are 5 possible rotations of that. And each of them would actually create a different order of operations, because in the order of operations we decide which number which number should be replaced. And when you replace something with a 6, there are 5 possibilities for that, and then we decide, then that decides all the future positions of 1, 2, 3, 4, 5. So additionally, if no numbers smaller or equal n are present, then answer should be multiplied by n because of rotations. Modulo billion 9. Questions? Time complexity is O of n log n for sorting, and then n times we run binary exponentiation in this time complexity. So this is log of max value. Was there a name for them? Gondola input sequence. Yeah. Without binary exponentiation, you could get 90 points or so, because the last subtask was just a few extra points. Okay. No questions? If so, then we move on to the next task. So I don't know if that will be heard, if you hear that and if it will be in the recording, but I keep hearing somebody disconnecting and connecting again. I'm going to quickly turn that sound off for me. Sound settings, notifications. User join, user leave. Viewer join, viewer leave. Okay. Should be good now. Next, problem friend. A very nice problem. I think this is the best problem from that IOI in terms of how simple it turns out to be, even though it's difficult to come up with a solution. Why do we need to multiply by n if there are no numbers less than n? That's because, let's say that what you see is a sequence 6, 7, 8, 9, 10. This is the input. N is 5. Then those operations described in the problem statement. Okay, so there is here, it seems, unique way of what we will do. On the first slot, we put 6. On second slot, we put 7. Here we put 8, and so on. So it seems that answer is 1, question mark. But the operations, let me open the problem statement. Replacement sequence. Sequence consisting of the number of gondolas that have broken in the order in which they break down. In the previous example, the replacement sequence is this. Okay, so the replacement sequence consists of gondolas to be replaced. And the thing here is that when you put a 6 here, you don't know what gondola is replaced. No? If this is the case, if this is what we are given, then you know that 6 replaces a 4. This is 2, this is 3, this is 4. So 6 replaces 4, easy. But for that such case, depending on the rotation of starting numbers 1, 2, 3, 4, 5, 6 will replace a different gondola. So the operations can be 6 replaces 1, then 7 replaces 2, 8 replaces 3, and so on. That's one way. But another is that maybe 6 replaces a 3, then 7 replaces 4, and so on. There are 5 possibilities of how we start. If no numbers from 1 to 5 are present, then the first move has n possibilities of what it replaces, and that fixes the rotation the starting rotation that we don't know. Hence this if. So if minimum is greater than n, you need to do this, modulo billion 9. Okay, friend. One more time, I will try to re-plug in. I'm guessing that my cable connecting me to the drawing tablet is broken. Well, mouse it is. In the task friend, there is oh, yay, it works. Yeah, computers are strange, but I will not complain. There are many subtasks, and I want to briefly discuss them, because it's a difficult task. For majority of people, you cannot get 100 points here, and you should be solving subtasks. So somebody creates a graph one by one. If there is already some graph, not all graphs are possible, but if there is some graph, then when new node comes, there is new node, it has some kind of host, parent node, and it inherits edges from it, depending on the type. It can be just directly connected to it, or it can be connected to neighbors of that host node, so it copies the edges, or it can be connected to those same nodes plus the host as well. Those are 3 possibilities. By the way, because of that, the number of possible, I don't know how to estimate that, but not necessarily all the graphs are possible. And then once we have the final graph, we are interested in max possible sum of values of nodes that don't touch each other. So max sum of independent set. Okay. First subtask for 11 points. We just build a graph in any way, and then check 2 at power n possibilities or subsets of nodes, iterate those. Each of them just check in n squared whether any 2 of those are connected with an edge. If so, this is not independent set. So time complexity 2 at power n times n squared to check. It can be done faster. I think it can even be done doing this recursively, and with bit masks we can do it in 2 at power n, but whatever. This is fine. So that's first 11 points. Then second and third subtasks are very strange because they are only about understanding the problem statement. If always my friends are your friends, this means that we are creating a clique. So this will create a graph where everything is connected to everything. So you can just take a single node, which means that you need to print the maximum from the input, maximum value of a node. Then similarly, if we are your... No, sorry, I described the other one. What I described is we are your friends. This one creates a clique. For this one, my friends are your friends, it will create no edges. Yeah, so here, no edges, so you can print the sum of all values. You can take everything. It's all positive, I think. Yeah, values are positive. Then, fourth subtask, let's leave for last, because it's actually similar to the full solution. And let's briefly discuss the fifth subtask. In this one, always we either are connected to the node, or to his neighbors, and that creates some property. So I'm connected to you. I might be connected to nothing if like I choose a node. If I choose as host somebody who doesn't have any connections, then this will happen. Then I can be connected to something. I can be connected to something. I can be connected to neighbors of that something. Anyway, the property that is being created here is called bipartite. We can split the nodes into even and odd, such that even and odd do not touch each other. Inside of even, they are not connected to each other, and so that's the thing with odd. Here's a quick proof. Bipartite means that a graph can be connected into two groups such that edges only go between the groups. If a new node is directly connected to something, then it can just go to the other group. So it would go here to the opposite group. And if a node has some host and it's connected to neighbors of that host, then this node then can just be added to the group with a host because it's connected to the other group only. That's a proof why the graph is bipartite. And with all the values being 1, what we're looking for is max independent set in bipartite graph, and that's solvable with bipartite matching. So you need to implement some bipartite matching algorithm, and the answer is number of nodes minus size of the matching. Size of the matching you can compute in O of n times square root of number of edges, so like n squared, n cubic. Sorry, this is n squared, so this is n, so this is O of n squared. Even slower algorithms should pass. In practice, matching is faster than it seems. So the limit here also could be bigger. Solution to subtask 5 for 23 points is bipartite matching. Now, let's move to subtask 4 and 6. In subtask 4, every new node is directly connected to one existing node. So what is being built is a tree. Every node has some value, and so on. And we need to find the maximum possible size of independent set. Still, it seems to be matching. Maybe some kind of flow can solve that for small enough n. But because it's a tree, we can run bottom-up dynamic programming. And I will actually describe it in detail because it's similar to the full solution. And I think it's very surprising that it's similar to the full solution, because full solution is not for a tree, it's a general graph. And to be honest, I remember that many years ago I tried to solve this problem, friend, and I couldn't do it. I didn't get the idea for 100 points. Okay, so how do we solve this easy subtask? Well, for every node, it's bottom-up DP. For every node and its subtree, we want to know the best possible sum if this node is taken and this node is not taken. Is there O of n solution to subtask 5? I don't know. I don't know speech. So you create something like this. You can also run a recursion, and you can make recursion return a pair, whatever you prefer. dp of v0 is max sum of subtree if we don't use node v. dp of v1, max sum of subtree if we do use v. There are two ways of implementing this, and depending on which way you choose, it will be slightly easier to do the full solution for 100 points. For a node, if you want to take it, then all the children should be not taken. So dp of v of 1 is equal to the confidence value at v. I will call it A of V, this is the number given in the input, plus the sum of dp of child 0. And if you don't take a node, you take the sum, and for every child, so if you don't take this node, then you are allowed to take any children, but you don't have to. Maybe a child shouldn't be taken because something in its subtree should be. So it's maximum of the max of dp of child 0, dp of child 1. So it's this. And you can run DFS for this tree to compute that. And for that, you should first read the full tree. You need to first read everything. You have a tree, then run DFS from the starting node, the node 1 or 0. Okay, that's way number 1 of implementing. Way 2, which is, I think, closer to what we will get for the full 100 points, is that we can keep replacing nodes and erasing them. If you know for a node, if you know if it's not taken, then the dp value is something. If it's taken, then dp value is something. If you know this value, you can use it to update the parent one by one. So let's say we have something like this. It's for 0 is 0, for 1 it's 5. Right? Initially, if you take a node, you get a value of 5. But when you see this child, then it can just affect a parent. You know that a child can increase you by 3 if you decide to take the child, but this can happen only if you don't take yourself, the parent. So this 0 will be increased up to 3, and then you forget about this child. Now in this node, if we decide not to take this node, from the subtree we can get the value of 3 so far, and if we take it, it's the value of 5. This also starts at for 0 it's 0, for let's say it had some bigger subtree already. And for this node, then if we decide not to take it, we get a 3. If we decide to take it, we get an 8. How will this affect the parent? Well, if we don't take parent, we are allowed to take whatever from the child. So maximum of 3 and 8, that's 8. So we increase this up to 11. And if we do take this node, the parent, then the child we cannot take. So 5 increases by 3, that's an 8. Poto.js, why in bipartite matching we cannot just take one half? Because the halves can be irregular. Think about something like that. This is counterexample to what you're saying. Oops. This is such a graph that your greedy solution would get 5 nodes, this or that, but actually it's better to take those 8s. So yes, in particular you are allowed to take just one half, but maybe by deciding not to do part of one half or one part, you have more possibilities in the other half. The idea of bipartite matching is it finds some kind of connections between the halves. In this case, it's trivial because it will just find this connection, and it kind of is saying, yeah, things outside of it for sure can be taken, and inside of my matching, the connection, I can choose only one node per edge. So I will take this, what am I saying? I'm stupid. This is not matching here. This matching will be this with that. And now we can take everything here and one node per those chosen edges. Okay, now back here. Okay, so the logic is, according to this, that we don't need to look at all children at the same time. Instead, when I see a relation child and child is already done, then I do something like this. for a node, its zero value gets increased by maximum of child can be not taken or taken. And if I decide to take a parent, so the parent is used in independent set, then the child cannot be used. By the way, this problem, this subtask, is very easy example of bottom-up DP on a tree. So, you know, whatever you do, it will work. There are problems where there aren't really such two ways, and it's more complicated what you're doing. You should merge children one by one smarter. But here it's easy. Okay. Now, full task, which is not an easy one to come up with. So now, graph is not bipartite. We have 100,000 nodes, and what can we do? Turns out that we cannot create the graph. We cannot greedily, as things come, decide what we should take to the independent set, because it depends on future queries. So what do we do? Still, we have the relation of every node is connected to its host. So we still have a tree. Yes, ways 1 and 2 are similar. Those are slightly different implementations. Like here you can run DFS for all children and then make a for loop to sum them up. But those are two very similar ways, I agree. So what I'm going to do, let's see the example. We have some example here. I'm going to copy paste this. As I'm given this information, I will build a tree. The main host is 0, so 1 is connected to 0, then 2 is connected to 0, 3 is connected to 1. By connected, I mean it's a host. 4 is connected to 2, and 5 is connected to 0. So I get this tree of dependence, relation, something like that. But actually, every edge is of some type. Some edges are the standard I am your friend. So this one will likely be easiest to handle because that was already our previous DP. But there are some that says my friends are your friends or we are your friends. So for example, okay, 1 is connected to 0 and this is really an edge. So this is actually an edge. Then 2 is connected to 0, my friends are your friends. So actually the edge that is being built is this one. 3 is connected to 1, we are your friends. So that means that 1 and its neighbors are connected to 3. Then 4, my friends are your friends. So 4 copies neighbors of a 2, 5, 0, I am your friend. Okay, so this is a graph. And you might be tempted to then just forget about those host edges and focus on this graph, but it's very hard. For general graph, I don't think this problem is solvable. We need to rely on the information that we were given, which is this thing. So it's a tree. And I'm going to use bottom-up dynamic programming, very similar to this one. That is, for every node, I will know in its subtree, still I can say that something is a subtree here. So I can have a subtree of 1 and 3. I will know what is the max sum if I take the top node, the 1, or I don't take it. Because it turns out, thanks to how regular those operations are, we can still propagate from child to parent, we can merge. And you can think about it as merging 2 nodes into 1. This is why on here I explained it in 2 ways, because in way 2 it was more like when I see a child, it already has some DP values, and I see a parent, I can say that this one is propagated here, and then I forget about it. I remove it from the graph after doing that. And I will be able to do it because usually, or kind of always, this node either it's directly connected to it, or it has the same edges, and maybe to a lot of other things, because it's not actually a tree of edges. But it has same properties, so it has same neighborship. If this node is taken, in order to erase it, I will just say kind of that this node is taken. Let's see examples here. Okay, so we already discussed the normal edge of just I am your friend. We have two more things to consider. One is the following. There is child, I will call it C, and there is parent node V. And let's consider the operation with name we are your friends. So C is apparently connected to V. V is connected to some other things that we don't care about. And those connections can then later create cycles, whatever. And C has the same connections. So how should we propagate dp of this child to parent? So how do I update dp of v1 and the dp of v0? Okay, because of this edge, I cannot take both v and c. What can I do? I can take v, and already this was some value. Then I shouldn't take c. So this becomes dp of v1 plus dp of c0. Or what also is possible is that I take c and I don't take v. So here I use a dimension of 1. Here I use a dimension of 0. But I will, when merging those two nodes, I will pretend that v is taken because they have same edges. I want to erase this thing from the graph. And for that, I want to tell the neighbors, hey, you neighbors shouldn't be taken because I'm taken. So this one will be here. So what this means, before I continue with formulas, is that if there is child, let's say it's a leaf. It doesn't need to be, but there is something here with value 100. There is a parent with value 7. They are connected with an edge. Parent might have some future edges that we don't look at yet, but child has the same edges. When looking at this child, in order to forget about it, I'm going to say that actually I can pretend that I'm taking this value, and the value here will be 100, and it actually represents taking the child, but the child had the same edges, so I can pretend that I took this guy. Okay, so it's maximum of this, comma, dp of v0 plus dp of c1. I can take the parent and not take the child, or the other way around. Both result in me pretending that the parent is taken. Then, if the v should not be taken, then I think it's easy to make a mistake here, but you shouldn't take this one, but also you shouldn't take the child, because taking the child means that all the edges now should be forbidden, all the neighbors. So in order to remove this from the graph and removing everything here, you need to then say that this is a 1. No, it's not this, right? Yeah. So 0, 1 and 0, 1 propagate to this, 0, 0 propagate to this. You don't have a transition that looks like this, because in We Are Your Friends, the parent and child are connected with an edge, so they cannot both be taken. This is forbidden transition. You cannot do that. You only have those. Of course, you do that at the same time. So new value of dp should be this and that. Those are old values there. Okay, and then there is the other operation, my friends are your friends, where there is parent v, child c, and the difference is that while edges are being copied, there is no edge between them. So it is this time possible to take both of them, and then we will pretend that v is taken. So I'm going to copy this and add one more possibility here, and that's dp of v1 plus dp of c1. And that's it for this transition. After doing that, you forget about node C. So that's it, problem solved. bottom-up 3DP with this transition for my friends are your friends, this transition for we are your friends, and this transition for I am your neighbor, I am your friend. Time for questions. The time complexity is linear, O of n, which is surprising given such small limit for n. Why this? You mean this one? You allow a possibility that V is not taken and C is taken. That this is allowed. Generally, you in each operation in your transitions you should consider 4 options. Not taken, not taken, taken, not yes, and whatever is the 4th one, you know, 2 times 2 possibilities. If there is direct connection between them, then you cannot take both of them. Okay, so again, very nice solution, I think. Very nice problem. Hard to come up with, but the code is very simple. What if V has some other edges which were added after we merge with C, so they don't have the same edges? Right, it's important that I guess I should have said about this. As we need to process everything backwards, so not just from the bottom of the tree, but just in reverse order of edges being created, so that we could always say that we erase a child and it's being compressed into a parent, it doesn't exist anymore. And if we do it, Yasin, then what you're asking about doesn't happen. I will make a screenshot to answer that. So the question, and it's a very good question, what if V has some other edges which were added after we merged with C, so they don't have the same edges? In order for me to say V and C have the same edges, I need to guarantee that all other things, they were already compressed into V. So if V has multiple children, C1, C2, C3, I'm talking children in terms of being a host, and if that was the order of how they were being created, then I need to work backwards through them. So I first consider C3, I merge it into a parent. Then I consider C2, I merge it into a parent. Now at any point when I consider this relation, it's the current tree, the current moment that I'm considering, it corresponds to the moment when C2 is created. So it actually does copy the exact edges of V. Yes, in the future, V might get some strange new edges because of C3 and future children and some future operations down there. But as we go backwards, this doesn't happen. Maybe I'm able to, can I use Control Z here? Oh, I can, that's great. So as I'm creating this graph, this is the sample test. When I first do this, then that, and so on. And now when let's look at something that might be an issue. That's 3 versus 1. If we look at node 3 and node 1, they don't have the same edges. We cannot start by looking at node 3 and compressing it into node 1 and doing this transition. Wait, they do have the same edges, don't they? 0 to 4, 0 to 4. That's unlucky. 2 and 0. Okay, I found it. 2 and 0. I cannot, even after I erase a 4, it's not allowed for me to compress 2 into 0 because after 2 was created, some later time, 0 got additional edge into 5, the green edge. So I cannot say that 2 and 0 have the same neighborhood, even after I am done with some bottom part here. But it's important that we go backwards through the objects, so decreasing number of nodes, instead of just DFS that visits children in any order. And now, given this graph, I need to first look at the node that was created last, which is 5, and I merge it into a parent. So DP values of 5 update the DP values of 0, which erases this. Then after erasing this green edge from 0 to 5, I look at node 4, and I do something with it. It updates into 2. Then I look at 3. I update it into DP of 1, and so on. Then I look at 2, and always it's guaranteed. When I look at a node and I merge it into the parent, it is guaranteed that this is the point corresponding to moment of time when this node was created. So it is true that edges of 2 and edges of parent of 2 are the same. So if you just implement DFS that visits children in random order, that's incorrect. Either do DFS but visit children in reverse order, so from right to left. I assume that's the edges you created, that being a host, you push back to a vector one by one from left to right. Or I think what you can also do is avoid recursion. You can have a parent array. This is the host. And just make a for loop from the end to the beginning. Merge I into parent of I. No recursion, no DFS. Both of those will guarantee that we do things in backwards order. So again, thank you, Yasin, for the question. Anything else? That was task friend. And we are left with holiday. I always print statements on paper. It's easier to think about them for me. Okay, holiday was the most difficult task. So the plan is to discuss the solution, and it uses something where I will discuss another Polish Olympiad problems. Not another. I will discuss also a Polish Olympiad problem, meteors, from like 10 years ago or so. And if you already know that problem, you can leave for that part. So just like yesterday, it will be an optional lecture to some of you. This time, it's more advanced. Lazy propagation, I think, is more basic. Though it's not a difficult algorithm. So this, then parallel binary search. Okay, what is happening here? We have a sequence of cities numbered from 0 to n-1, each of them with some score. Score the number of attractions per city. So there is n, there is sequence of values. Maybe, do I care about indices? Yeah, let's say I do. And here there are some values. Those are indices. I will mark them with a color. Though this is sequence AI. And those are indices. You start at some particular position given to you, and you can go left and right. Every second you go by one to either side, and you're allowed to visit attractions in the given city, and you visit attractions all at the same time. Wait, so is it number of attractions or is it the attractiveness? We spent 1 day to visit everything in a given city, right? Yes, okay. So starting from here, one possible strategy would be the following. We get the score of 7, then we move right. We get a score of 5, then we move right. We don't do anything here because 1 is not worth it. We move right, then we get a score of 3. Then we move left, then we move left, then we move right. That would be wasteful, but then we move left, 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 and we get a score of 4. Something like that. So in one operation, either move to I-1 or I+1, or get score AI. So score plus equal AI. You can do this only once per city. When you do this, AI changes into 0, let's say. You are also given D, the duration of your trip, and question is max total score in the operations, question mark. There are also subtasks which I think are worth discussing. Yeah. The task is holiday. I'm not sure about first subtask, how much we gain by iterating a submask, but I guess it can be done. So to solve the first subtask, we can iterate the subset of cities that we want to visit, and then we need to find optimal way to move between them to check if we can visit them. But in order to move between them, I need anyway an observation that allows us to do future subtasks. Maybe it's more like DP that has a mask of what was already visited. Yeah, I'm not sure what was intended here. But I believe that subtasks 2 and 3 are similarly easy. So let's go for those. If you start from anywhere, it's easy to guess or prove that you will for some time move to one side, and then you will move to the other, and that's it. You will not do other things. I don't like that I use the same color. So you just will move one side, then you will move the other side, and that's it. If you know the rightmost and leftmost city that you're going to be, it's optimal to first go to the closer one out of those two, because that's the distance that you will double. So if you start at starting city S, I don't know what was the actual name, starting city S, and this is L, this is R. If you first go right, the time you will spend on traveling is R minus S plus the total distance of R minus L, but in other words, that's S minus L plus twice the distance of the right part. Right? This distance we cover twice. Yeah, or in other words, this is distance left plus twice distance right. If it's the other way around, then it will be 2 times distance left times distance right. That's the time you need to travel, and the remaining time, which is D minus that, this is your time to actually visit cities, to visit attractions. Let's call this X. This is time that you have to visit attractions, and among the cities that are available to you, you will choose the maximum X of them. Max X values inside of this range. So a polynomial solution is the following. Iterate L from 0 to S. Iterate R from S to n-1, the leftmost and rightmost city that you visit. Consider 2 possibilities, whether you first go left or first go right. You should do this with a for loop of size 2, and you can, reverse the sequence or something, including the position of S. You should mirror it to n-1 minus S. But I will, from now on, assume that we first go right without loss of generality. But you need to, in your code, consider the other case. Then x is equal to this, this thing. D right is r minus s. D left is s minus l. So we have this. Choose max x values in range L to R. And maximize this with 0. The sum of those is possible sum of attractions that you get. Time complexity n cubic. Right. So in particular it will solve subtask 1. Subtask 2, actually we start at city 0, so we don't need this for loop, but still this with that it will be n squared. So we are not solving neither subtask 2 nor subtask 3. But as we keep going into some direction, we can maintain the max x values in some data structure. And we have two main ways of what that data structure can be. Right. Right. So if you want to keep track of max x values, my first guess for that, my first attempt would be set or multiset or priority queue. So how to maintain top x values. Way 1 is set, multiset, priority queue, any one of those. So as I keep going into, let's say as I keep decreasing L, that seems, yeah. As I keep going L, and let's say I do it decreasingly from S down to 0, always I get one more node. And I can maintain a set of top x values. In such a set, I can insert a new value. I can also change the value of x. I think it will be easiest to explain using the second subtask. So this subtask. I'm sorry to those who already know how to do it and are waiting for the full problem. We'll get there. So if we start, at city 0, then as we keep going, we basically are iterating index r, the rightmost city that we visit. Because we know how much time we need to travel, then we know how much remaining time x we have to visit attractions. So as I keep going to the right, I keep discovering new values. So always there is some new value a of r that I need to add to my set or multiset. But also, the value of x keeps decreasing. Initially, if I don't travel at all for r equal to 0, then the time that I have for visiting attractions is the value of d. So I'm interested in top d values. But as I move there one by one, and I first say, oh, r is equal to 1, then I have one less time to do this. So as I move from r0 to n minus 1, I need to do the following. Set, insert, or multiset, or priority queue. Insert a of r, but also x minus minus. What this does is it limits size of the set into one less element. So I will do this. While set size is bigger than x minus minus, initially x is d. While this is bigger than x, set.erase smallest element. That's the solution for this subtask 2. It has a loop inside of a loop, but there is some amortized time complexity going on. In total, I will insert n elements to a set, so I cannot erase more than that. Yeah, so I will keep adding new elements to my set, but always the size of set will be limited to smaller and smaller value of how much time I have for actual attractions. Eventually, this might go down to 0. Yeah, so I guess this, remember to maximize with 0, or you can maximize it with 0 here. Okay, so this is it. Any questions for this subtask? For n up to 3000 and no starting city given to us, or no, starting city is given but it's not 0, we can do this as we iterate one of those things. So as we iterate L from right to left, given a fixed R, we can maintain our set. So subtask 3 is this. For every R from S to n-1, the order of considering them does not matter. You start by saying x is equal to d minus twice d right. D right was r minus s. So we know that we need to get from the starting city to the right to r and back. This is remaining time for attractions. And now as I move with L from S down to 0, always, I should here already have a set of elements from S to R. I guess I can maintain here, but also in this subtask it doesn't hurt to create it here. So set is create an empty multiset, and here insert values in range from S to R. So in your sequence you have S and R. All the values here are already available to us, and we know that we need to at least traverse this part. And now one by one, as I keep going through those elements to the left and I keep modifying L, I insert new values, so set.insert a of L, and I update X. And while something, I erase the smallest element from the set to keep track of the max X elements. This is n squared. Actually, we have 1, 2, 3 loops, but this last one is amortized time complexity. We will not be able to erase more elements that we inserted. And we inserted an element n squared times. Okay, so we are able to solve the first 3 subtasks for 47 points. And I think for a strong competitor, that's a minimum in this problem. Now, the intended solution uses something else here. It's not obligatory. We can finish and get 100 points with set or multiset or priority queue, but I will maybe first explain way 2, the one from intended solution. Maintaining top X values, more like querying about them. Way 2, segment tree. If you're interested in top X values, but in advance you don't know the value of X, that can be done with a segment tree, not very complicated one, but imagine this. If you have you have this sequence of values, let's say 5, 10, 17, 3, 8, 2, 2. Now, you shouldn't just build a segment tree over this. Like 5 and 10 shouldn't be connected into a parent that is 15, because this information is useless. It's not true that I should take both of those and the sum of them is important. It's not that I take range sum. Instead, I'm going to sort those elements. On the side, I still keep track of the original sequence, but for the sake of segment tree, I sort them. And I build segment tree, but not exactly with some extra information. So I have this. And in order to keep track of the number of elements, some kind of X, we know that among available elements we will want a suffix, but not all elements are available at any time. So we should be able to turn an element off and on. You can think that what we can do is we can change something to 0, or we can change something back to active element. I don't actually recommend changing it to 0, but in a leaf I would anyway keep, I think, this value. But every element is either active or not. And let's say that originally no elements are active, they are all of type 0. And then when somebody tells me in this previous way we would insert to a set, here we would activate a value. Let's say that I activate value 8. I say that now value 8 is possible. Also value 17 is possible, available to us, value 3, value 2, another value 2. And in order to move in this segment tree and to know what are top X values available to us, let's say that this is some fake element, infinity. In every node, you keep track of the sum of how many active nodes there are below. And to find top X values given a query about value X, you start from the root, and you always look at your two children, and based on that you decide where you should go in your segment tree. So let's say that X is equal to 4. You want top X elements. You're here, you're looking at your children, you know that those on the right are bigger. On the right we have two values. 2 is smaller or equal than X, so for sure those should be taken. Those should be taken. But I go left in order to search for the what is the boundary, where is the fourth biggest value. I again look at my two children and I say, oh, this child should be taken. Oops. Then I go down here and I will also take this one. Like this, in logarithmic time complexity, you can find top X values. And in order to know what is their sum, you also need to keep track of the sum of values below, sum of active values below. So the sum of those two nodes should be 8. So this is, I guess this, you can pretend that this is a 0. This is 17, this is 25, and so on. 3, 0, 3, something, something. Can we do this type of query online? Yes, we can. This is so we have decreased font, please. In segment tree node, we keep track of count active and long sum active below. I think in a node we keep track of those two values. And then this segment tree allows us to say activate value or deactivate. Deactivate, is that the spelling? And find kth greatest active value and find sum of k greatest values. Deactivate, thank you. And we do that by, it's kind of binary search in a tree. Starting from the root, you always decide if you should go left and right by comparing the value of the right child, which you prefer, with the remaining value of X. And if you here skip the two elements, then you also decrease X by such amount. I think you can, if you don't know this, you can search more on code forces at least. Segment tree, find kth smallest element. Yeah, I'm not going to find it now. I meant query like sum of top k values in range AB. There is no range in the query. No. This thing has nothing to do with ranges in the original sequence. I'm not querying. Query kth greatest element in range LR in the original array. Can that be done, by the way? Yes, with persistent segment tree. Persistent segment tree can do it. We go through this sequence from left to right, and it will be important at index R and at index L-1 what was state of the segment tree, and like that you can kind of perform binary search by going from the root of both segment trees. So you will simultaneously go down from the root of two segment trees. Each of that is a state of persistent segment tree. So I will say this is harder because the solution is this, but we will not do it here. By the way, now Now that I think about it, does it help? Maybe. Maybe this is one possible solution to our problem, holiday. But there are still some more things to do. Maybe it would lead to worse time complexity. Okay, but what we did is this thing. It's alternative to my set. Also in way 1, so I said way 1, this is also keep track of sum of values in set. So either we do this, in set we insert and we erase elements. In segment tree, we are more independent because we don't keep track of the value x. Segment tree just keeps track of active and not active elements. So how segment tree solves the task for 47 points? So we still do this. Maybe I will talk about some example. Okay. Let's talk about subtask 2 again for a moment. Seg tree solution. It was the one where we start from city 0. We have some values. We sorted them like in coordinate compression and built segment tree on the top of that. So we build segment tree like I described. Initially everything is deactivated, and one by one we here iterate and we consider every element that maybe this is the position to which we will get. So we one by one activate elements. If there are ties, remember to activate only one of those. So we have always such a position, and we got up to here. We can easily, with some formula, compute what is the current x, how many elements you can take among those already activated. It will be d minus the current index r. And in segment tree, you query what is the sum of max x values. Now, for difficult part. Holiday. Idea for 100 points. We don't know, we cannot afford iterating both L and R. So I know that for some time I will go right and then I will go left. But I cannot iterate L, iterate R. That would be n squared. So I'm going to do those two parts independently. Which seems stupid, but I will focus on the right part and I will say, I wonder how much score I can get for every thing like this. And separately on the left, how much score I can get for each of those. This already we can do, each of those parts in n log n with set or segment tree. But that doesn't help. Because when asking, for example, how much score I can get from here, you don't actually have d days for that. You have, depending on how many of those attractions you will use, you will be left with fewer days to visit attractions on the left. What actually I want to know from right and from left in order to be able to merge it is, depending on how many days you spend, what is your maximum total score. So I don't really care, and it's not properly defined, what is my max score on the right from this part, because it depends on number of attractions. I care, depending on time spent here on the right and to move back, what is your maximum score, including the attractions. So on the right part, I'm interested in answer right of 0 up to d, where answer right of lowercase d, that's max score spent on max score on the right if we spend d days. This is lowercase d, and I want to compute it for everything from 0 to uppercase d given to us in the input. I'm going to compute the same thing on the left, answer left of 0 to d, and then I will be able to just say that answer L of I plus answer right of D minus I. Let's say that we need to spend exactly D days in total. If not, with some prefix maxima, it's easy to fix that. The final answer will be maximum of those for all the indices I. But it's not easy to compute such an array. So we now, from now, focus on that. And as well, we can just assume that S is the starting city. And we only because we only focus on 1/2. Later, we should reverse the array so that we could run the same function and run it also for this part to compute that. So what we need to do is, given a sequence and starting city equal to 0, compute answer of everything from 0 to D. For every number of days, what is your score? There is some detail here that the left and right part behaves in a slightly different way because of this. So in one way, the actual number of days is doubled. Number of days spent on traveling is doubled. It's a detail that we can talk about at the very end. But generally, we compute this. Answer of D is max total score if we spend D days. So in 1/2, we actually need to also get back to the starting city 0, which changes one formula. In 1/2, instead of D minus R, we will use D minus twice R. How can we compute this array? There are problems where we need to compute optimal case for a lot of values of k, and there are different optimizations that can be used for that. Some ideas that come to mind are dp divide and conquer, and maybe aliens trick. Not really, so the Lagrange optimization, but also parallel binary search. Those are terms that are slightly related to us computing for a series of parameters what is optimal score. Aliens trick here, I guess that those two things are still related to aliens trick. Still, we here try some other parameter, and depending on that, we will go left or right. So it's not that far, but those are, let's say, related techniques. And what we will do is, well, some kind of divide and conquer, and how exactly you want to call it, it's up to you. We will use divide and conquer, and we will use some trick so that when going to every half, we wouldn't again be linear, which would be quadratic in total. We want to get n log n times logarithm from segment tree or a set. So I'm going to do the following. Let's say that I'm interested in all the values of D that belong to a range from 0 to uppercase D. I will first try the middle point, D over 2, and I will solve the problem. We know how to do it in n log n with set or with segment tree. So we have the starting city 0, and we consider that maybe this is the amount we travel, this is the amount we travel, and from set or segment tree in each of those cases, we know what is the score, and we know the total score is equal to something, 70. We can now go to every half from 0 to D over 2 and from D over 2 to D, but that is useless. So far, I only am describing how for every D to solve the score separately. Such a solution would be O of D times n log n. Very stupid. I don't want that. But instead, we guess, observe, or prove that the longer the value of D is, the further away we should get. So, intuitive observation, let's say, bigger D, number of days that we have, you should go further. I didn't think about the exact proof, but for me it seems intuitive enough that if you have more days available, it's never okay to suddenly shrink my current range, because then it would be also optimal to do it for a smaller number of days. Of course, formal proof might be difficult. I don't know, didn't think about it. This seems intuitive. During a contest, sometimes when you work with the last difficult problem and it's the only one, and you don't know if some observation is correct, you can use some brute force to check that. So you can use your n-squared solution and verify that for random tests and various values of d. You can compute how far it happens that you should go to get optimal score, and you should check the inequality, put that in an assert, and you will verify the observation. If I had enough time and I wanted to know if this is correct, this is what I would do during a contest, if I couldn't prove it in a minute or two. Okay, so actually related to proof of that, but also related to what we will do, is not only I will know the score, but I will know optimal R. Opt R is equal to something, some kind of index, maybe 4. It will tell me, given this number of days, how far you went to obtain the optimal max score. And we claim that smaller values of d, so those before that, will have smaller r's, bigger will have bigger r's. And it's the value that we pass in divide and conquer. I think that this is most common in divide and conquer DP optimization. Okay, so what we will have is a recursive function, because it's divide and conquer, that gets d low, d high, I will not specify ints, d low, d high, r low, r high, and that's it. Initially, we run it by saying compute it from 0 to d, from 0 to n minus 1. This is, we run this. We have such a function, and what happens here is we try something in the middle. We then, in O of n times log of n, find max score and opt r and opt r. So find for what r you hit the max score, and then run recursively for d low up to the d minus 1, for r low up to your opt r, and d plus 1, d high, opt r, r high. This is the solution. Remaining is to understand why this code is connected to this observation that I set. So why now this is true, and how actually this shouldn't be n log n. This should be dependent on this thing. So here I'm going to replace that with r high minus r low instead of n, because this will nicely sum up to O of n for every layer of recursion, and because of that this will be n log squared, log from this and log from recursion. Okay, so when I first try d is equal to d over 2, I will compute some kind of opt r, optimal r in this case, and then I will, for smaller d's, I will only investigate those r's, and I will stop my my simulation at this point. And then for bigger d's, if I have more than that many days, I will only try to simulate this part without resimulating that, which is kind of tricky, and there are different ways to handle that. So actually it's way easier to do it by iterating from 0 to r high, but we need to just iterate this range. If we're able to handle such a range only iterating those elements one by one, then, and let's say we ignore the fact that this position is included in both ranges, then for every level of recursion, and there are logarithmic levels of this divide and conquer recursion, the sum of sizes of ranges is linear. And always it's size of range times logarithm. Hence the total time complexity is n times depth of divide and conquer times this logarithm, so just log squared. This logarithm from using set or a segment tree. Right. And now, how do we actually only iterate this range instead of always going from 0 to somewhere? Well, you have two ways, at least two ways. So holiday, solution one. We use, wait, so do I use persistent segment tree? What was the memory limit? I mean, the intended solution does not use persistent segment trees. 64 megabytes, that's not a lot. 100,000 times log, it's 2 million. Times 2 times 4 should fit. Okay. I just wonder why they didn't use a set. Let me take a quick look. Oh, they move back and forth in segment tree. Okay. Segment tree thus moving back and forth, which requires us to turn things off and on in a segment tree. I will now explain this solution, but I will also give you a link to a blog and my comment that talks about this. So there is a blog called Parallel Binary Search. It explains this. It explains parallel binary search, and you can look at my code, my comment here, including the code, which is quite nice and commented, where I explain what exactly queries we cancel and what we add back. So I will give you a link to this comment. This is a holiday / parallel binary search back and forth solution comment. I mean, it's not, this talks about another problem, meteors, but I think it's a nice explanation. But for now, I'm not talking about meteors. I'm talking about holiday. So let's solve holiday. I think this solution is quite complicated, but let's try it. Initially, I iterate everything from 0 to n-1. For every new element, it means activating something in a segment tree. Then, let's say I restart my segment tree, and I want to do second level of this recursion. What I need to do, I will not actually restart, but what I need to do is go through this. That's not a good explanation. Okay. After the first recursive call, we went through all of that. Now what we can do is we can cancel some elements, so we can move backwards either to 1/4 or 3/4. Each of those elements we can deactivate in the segment tree. And moving backwards, we can go to any smaller recursive call like this one, passing or giving access to a global segment tree such that its state is the state of segment tree, let's say, at the endpoint of this range. And then this range will do something internally. So I'm going to copy this and add some explanation. That here there is some invariant. Global segment tree already has already activated. Includes indices 0 up to, well, at least are low activated. Depending on the implementation, different element will be here, but it's something like that. That is, imagine that we have 100 elements. But now we are in very small recursive call where we have just those 4 elements. What we need to guarantee is that there is that global segment tree, which is of size O of n, so it's huge. And all the elements from here are already activated in segment tree. Thanks to that, when you consider those, you don't need to again go and activate all of them. You just one by one activate this one and ask segment tree for what is the sum of top x elements. X is the thing computed with formula based on the number of elements here. Then you activate this one, you activate this one, you activate this one. This way, in O of just size of this range, you're able to simulate this part. Then you find here some opt-r, this way, and you want to run recursively for this part and that one. For each of them, you all want to satisfy this requirement. So in a segment tree, you deactivate, let's say, all of those, because you are here. Now the segment tree includes all of them activated. So you deactivate all of those, and then you run recursion for this part. This thing ends, and then let's say it's guaranteed that it's moved the segment tree back to this position. Then you need to activate them again one by one and run it here. So for convenience, let's say that here, after everything is done, there is again invariant that global segment tree should again be in same state. By this I mean those should be activated and nothing else. Can't we do something like BFS and for each layer we iterate over all elements in linear time? Yes, Yasin, that's the better solution, and I will explain it in a moment. So for this first solution, you want to be able to activate and deactivate. So you want to move left and right. And again, the link that I posted and this comment explains something like that. And there is information what range of queries we are investigating, and then what queries we cancel and what we activate. This is the exact description. So, and because that comment exists, I will not go into detail about implementation of that thing. Still, this is solution 1, segment tree, where for every recursive call moves through some number of elements only for this current range. Holiday solution 2. Now, this is not described in the official editorial, but actually parallel binary search or divide and conquer for ranges, stuff like that, can be implemented basically without recursion. So helper question, how to implement divide and conquer without recursion? I mean, divide and conquer actually requires us to do short ranges first, but that also can be done. Instead of, so we start from range 1 to 100, then we will do 1 to 50, 51 to 100, and so on. And we have this binary tree of recursion. But instead, what we could do is just one by one iterate one layer, then another layer, and so on. Usually in divide and conquer, we do it from the bottom. So in this layer, we would first do something with a range from 1 to 50, then do something with a range from 51 to 100. Turns out that this idea can be implemented here. That is, and that's one way to do parallel binary search. Again, we do something equivalent to this. So our target for every D in range from 0 to uppercase D, compute answer and opt-r. Opt-r is just helper array, so we would be able to do stuff faster. But this is the actual target array to compute. Okay, we first iterate from 0 to n-1. We simulate. For every position r, we know what is the score in that case. Of course, we're doing this. We will find some kind of opt-r. And then we will know that this is opt-r maybe. We know that for smaller Ds, we need to move here. For bigger Ds, we need to move here. For bigger values of D. In some way, we need to save this information. So let's say the information is saved that range of D belonging to from 0 to D over 2 minus 1 needs to happen here for range of R from 0 to opt-r. And there is also here some range of this. And then what we do is we restart completely our segment tree. We clear it, change it to zeros. I mean, leaves can be the same, just we deactivate everything. And we again go from left to right. And always when we are in some range, we should know what values of D are interested in that range. And because of that, what is the middle value of D that we investigate. So as we iterate here, at every moment we will ask segment tree using this value. So we activate this element and we ask for top X elements, assuming that this is number of days that we have. We go up to here, and so on. And in this process, some position gave us the best score, the best sum of max X given to us by segment tree. Let's say it happened to be here. So this is the new opt-r. And for the next layer, we need to say that this is a range where D up to D over 4 minus 1 goes. This is a range where next quarter of these go, and so on. And as we move with segment tree, we are not going to do anything smart with segment tree here. It's just that we switch to now caring about this value, but this value only affects a query, not the segment tree. So then after activating this element, we activate this element and we query using that. We activate this element, we query using that, and so on. I guess this is a point where we query about both this D and this one. And we get shorter and shorter ranges. The ranges might not be of same size. So it's not that every red range of values of R is of the same size, but the important fact is that the sum of sizes is linear. And that's true even if they intersect by 1 in each of those slots. Right. Oh, and now, fun fact is that this solution works both for segment tree and for our set/priority queue. But the set/priority queue is slightly more complicated because of what is happening here in this position. In this position, D increases, so we actually need to add back a lot of elements to the set. So, fun fact, solution 2 can be done with 2 sets, not 1, instead of segment tree. Always when you start here at the beginning, and you will do it logarithmic number of times for every depth of divide and conquer, you will iterate this. Every element you will activate, so insert to the set only once. But you need to have a set, well, actually multi-set, top X elements. You also need to have a multi-set of those not top others. Always there is some kind of current value of X, current value. And always when you move to the next index, it changes by 1. By 2 if you're in the half that is doubled in terms of travel. Okay, so for every new element, you add something to one of those multi-sets, or best always add here, and if the size of this set is too big, then add it here. And from time to time, the value of D will change, which will affect the value of X, which will trigger a lot of modifications. But in total, the number of the total sum of differences of D is linear. So it will not grow the time complexity to quadratic. So something like this will happen. Top X insert I of, or maybe this, for every I. Top X insert I of I. Then update X a little bit. While top X size is bigger than X, then move smallest from top X to others. But because from time to time X changes a lot, it will happen at every such position where this new range starts. Then also we need to do while top X dot size is smaller than X, move move biggest from others to top X. This is how you can maintain top X elements in a set. Also, you need to keep track of the sum top X, initially 0. Always when you move something here or here or here, you need to update that value. And normally when you have a for loop and inside of that there are loops that move something in 2 different directions, then it can be quadratic. But it is true that the total difference of how much X changes is linear. Because every time when you move by 1, X will change by 1 or 2. And you move from one D to the other, that thing only increases, so in total it will contribute to movement by uppercase D. So it's good. So here's a solution without segment tree, surprisingly. All right, that's it. Time for questions, and what will happen next is I will talk a little bit more about parallel binary search using problem meteors as an example. And if you know it, if you know Polish Olympiad meteors, then you should leave. So there we will discuss solutions with so you can read linked comment, the one that I sent to you. That's first thing, but I will explain the BFS style parallel binary search. And finally, I will mention persistent segment tree, which also solves that problem, but with worse memory. So it's a little bit worse. Parallel binary search. Okay. And if you don't want to listen to this, you can go. So problem meteors. I'm opening the problem statement. Here is the problem statement if you want to solve it later. And the problem is like this. There is a sequence of, how is it called? Sectors. There is a sequence of M sectors. Can you explain Holiday a bit more? I don't understand how you update the answer. How I compute this? That's the trivial part, which is basic n log n. But sure, I can, I guess, summarize. So let's move this for later. So summary of Holiday solution is as follows. We have some starting city. We will run some algorithm for the right part and for the left part. In every part, I want to compute, depending on the number of days I'm allowed to spend in this part, what is the possible max score. Also, we need to behave differently for the part where we go back and forth. So I think actually for every part we need to run the algorithm twice. Right? So we, for example, focus on right part and we say that we will move somewhere and back. So we will apply the same algorithm a few times, also for reversed array, but now we just focused on the start being the first city. And we just go here to the right, and possibly, depending on a Boolean flag, we need to go back to the start, because actually there are more things on the left, and we need to go there. I need to compute an array of answer of 0 to uppercase D for every number of days. What is max total score? Because I might want to spend some number of days on the other side of the starting city. I need to compute this. In order to do it, I will do divide and conquer on, depending on the number of days, how far I will go, or the other way around. Depending on how far I will go, what is the number of days? The first description is slightly better. I first investigate number of days equal to uppercase D over 2. And I will simulate something in n log n from left to right using segment tree or a set. And I will, only having activated those elements, I will ask for top x elements. X will be always computed as the D minus the distance. So this D, number of days, minus the distance, multiplied by 2 if I wish to go back. So I will ask segment tree or set for top x elements. I compute it for here, and let's say the segment tree told me 20. I compute it for this part, segment tree told me 30. I compute it for this part, segment tree told me 40. Up to here, 45. Up to here, 30. Up to here, 32. I'm guessing that it will be bitonic, which means increasing and then decreasing, but I'm actually not using that property. But there will be some maximum. Maybe there are ties, then I take any one of those. So after n log n computation, I in particular know for this number of days that I have, what is the max score? That's 45. And in particular, I will save it. I will say, okay, answer of this particular value of this equal to 45. But I also will save, for the sake of divide and conquer, that optimal R is this index, up to which I apparently got to get 45. And now I'm guessing I have the following guess. If I have fewer days, then I will not visit those cities. If I have more days, then I will certainly go at least here. So those should be activated anyway, and I will only continue going there. So I'm going to run my divide and conquer. only for this part, investigating a range of days from 0 to d over 2 minus 1. And for this range, investigating a range d over 2 plus 1 up to d. And then there are different ways how to implement this divide and conquer. The easiest one would be to go layer of layer, depth by depth of this recursive divide and conquer. And I think still we can just now discuss meteors, because that explains this technique. I hope this helped a little bit. So now let's talk about a well-known problem. Where was the statement here? There are M sectors and there are events. Sometimes a range of sectors is increased by X. And also every sector is owned by a country. And we need to, for every country, know when it will be satisfied. That's the problem. Limits up to 300,000. So there are M sectors, each owned by one of N countries. You're given a sequence A of M of ownership. So for example, the sequence might say 1, 4, 2, 3, 1, 1, 1, 2. And this means those are sectors owned by first country. Those are sectors owned by second country. This is by third country, this is by fourth. There are events that say for some range, every sector gets increased by X. Not this value. Initially, there are 0 meteors on every position. So initially, every sector has 0 meteors. And now there is a rain of meteors. Everything in this range gets increased by plus X. And then every country gets some meteors. If a country has 2 sectors in a range, then it got twice X meteors. Every country gets meteors that land on their sectors. For every country, we need to decide when it will reach some threshold. For every country, there is some threshold of how many meteors they want. Find out when it happens. When the country gets satisfied, after which range. And we will not solve this problem online. There is no segment tree that is able to increase range by plus X, but handle the fact that in this range there are many owners. And for each of them, actually, we need to increase it by X, and we need to check if some thresholds happen. No. Instead, for every country, we will do kind of binary search, which also can be done with persistent segment. So, solution 1, which actually will give you memory limit exceeded, I think, is persistent segment tree. I will briefly discuss it. For every country, from 1 to N, we're going to binary search the time. So the time is time can be from 1 to the number of queries, Q, which is, I'm guessing, also 300,000? Yes, K. So we binary search the time when the country should be happy. And inside of this binary search, we need to check after, for example, the first 6 range updates, is this country happy? So I'm going to here say for every sector among sectors owned by this country, let's say we collected that for every country, we say total plus equal ask segment tree for this sector at this time. Initially total is 0. And then you can check if this total is enough. If total greater equal threshold for this country, then in binary search go down, else go up. Down means that now this country is happy, maybe it was happy earlier. Time complexity of this solution is n for countries, log of time here, so log of number of queries. And here we iterate sectors owned by a country, but if for every country we iterate all its sectors, in total it will be O of m, number of sectors. So this highlighted in total is O of m, and we multiply it by the time, so it's log of number of queries. Also we ask segment tree, or persistent segment tree here, so it's log of m. This is the time complexity. We need persistent segment tree because at some time, so after some number of updates only, we are interested in the value at this sector, which can be done. The disadvantage of persistent segment tree, first is you need to be able to implement it, though I think it's not that hard. Second is that it has bigger memory. It will have a memory equal to, well, there are m events. Each of them adds extra log of n things. So this is space complexity, memory or space. And I believe that it was not good here. 300,000 times 20, that's 6 million. And 6 million ints would be okay, because that's 24 megabytes. But those are not just integers. I'm guessing, do I need longs? I guess that we can be fine with ints, but those are inside of vectors, inside of nodes of a segment tree. So the constant factor will be significant because of vectors and the fact that we push back. So I would expect at least ×2 because of vectors, and in practice it will be more. Maybe then this can be squeezed, but yeah, it's not easy, I think. You need to do a lot of tricks there. So maybe this can be done. But now we will move to something else. Okay, so we will try to binary search for all countries at the same time. For every country, we want to binary search when this country is happy. And that can happen in time between 1 and q. I'm going to ask what happens at time equal to q over 2. And for all countries, I will decide whether they are happy or not. So say that there are k equal to 10 updates, range updates. Then we first ask at time k equal to 5, we check all countries. So we have a normal segment tree that is able to increase the range by something. In normal segment tree, we simulate the first 5 updates. We say this thing plus equals some x, this thing plus some kind of x, this thing some plus x. We do it for first 5 ranges. And then for all n countries, for each of them we check all its sectors, add them one by one, and we figure out, oh, country number 1 owns this sector, this one, and its sum is 100, and it's bigger equal than its threshold. So this country can be happy earlier. Then country number 2 is here and there. It has the sum of meteors 20, and it's smaller than the threshold required for this country. So actually this country needs more updates, more increases. So it should be done later. We split countries into those that might be satisfied before k equal to 5 and after, which is basically first step of binary search for each of them. This solution, for every country it binary searched by first asking what happens at k over 2. So like after 5 out of 10 things. So the name parallel binary search means that for a lot of objects you binary search at the same time. For each of them, you decide if it should go left or right. And just like initially, every country starts with binary search range from 1 to k. One by one, you will update it. Thanks to us asking what happens for everything for k equal to 5, for each range, you will update the range where we should investigate it. Everything will be either on the left or on the right. Maybe 5 will be included, whatever. So yeah, let's say this. And now, next, we will group together all things that are interested in the same range, like those. And those countries now should be queried at time 3, versus those countries should be queried at time 8. So I'm going to now, for the second time, start with a sequence of zeros, and again simulate all the updates. I perform the first update. In some range, I increase plus x. In some other range, I increase plus x. So I go from the input range updates. And whenever I hit one of numbers that now are interesting, here it's a 3, for some countries want to know if after first 3 range increases, they are satisfied. So for each of those countries that are saved for such value, we need to now iterate. For country 1, I iterate sectors owned by country 1. I compute the sum, and depending on that, I will know if I should update this into 1, 2 or 4, 5. I perform a step of binary search for this country. And and after that, I will continue simulating the process. So I applied first 3 range updates, then I perform 4th, 5th, 6th, 7th, 8th. After that, I know that there are some countries interested in that, and I continue. I need to repeat this process, simulating from the beginning to the end and then restarting with a sequence of zeros, logarithmic number of times, because I know after that, every country will know exactly when it's happy. So we start this. For every country, save its range, its binary search range is equal to 1 to k. And at time k over 2, we're interested in what happens for this country. So interested of k over 2, push back this country. This country is one of those that wants to know if it's satisfied at this time. Then repeat log of k times, rounded up, so just repeat 20 times this. Start with sequence of zeros. You build segment tree on the top of that, so that you'll be able to increase range by plus x. For every index 1 from 1 to k, this is index of range update, increase ith range, the one from the input. And now for all countries interested at this current time, you want to compute its sum. So total equals 0 for sectors of this country, total plus equal query in segment tree what is at this position. And then depending if total is greater or equal than threshold of this country, you go up or down. If total is enough, then you go down, else you go up. What down and up means? You update its range. So in both of those cases, you update range of this country is equal to new thing. And also for the sake of next iteration. So you want this iteration to happen, to finish without caring about this country again. I guess it doesn't hurt to push back to some future interested. Yeah, but I would make a copy of this to have a second array of vectors. So interested prime of some new position, which is the middle of a new range, dot pushback of this country. This is what you do. And depending on down versus up, you use different range. Time complexity, O of log of k, and then you do k things. Each time you do something in segment tree, plus always you iterate countries, and inside of every iteration, every country will be considered once, and its sectors will be considered once. So here it's just, there is no logarithm here, because here there is m, number of sectors, multiplied by log, because for every sector, there was also log here because of range update. Yeah, so this is time complexity. In total, log squared again. Time complexity didn't change. The code did. And I will give you one more link. There is a comment that explains that shortly, so you can read it later again. So this is meteors, parallel binary search by iterating log of k times explained. So this is a comment that talks about what I've just explained. The comment I gave you earlier, so this one is slightly more difficult. It's a different implementation of parallel binary search, but it's the one that organizers intended for Holiday, though both can be used. I think it's beneficial. It's important that you know at least one way, either this one or this one, but you know, this one is simpler. Time for questions. If you want something very advanced, then eventually you should learn DP optimizations. There's this blog about it, DP optimizations blog. I'm pasting a link. And it includes divide and conquer optimization, which boils down to the same thing, which is in some part of our algorithm, we can say that depending on one parameter, the other optimal parameter will increase. It's monotonic. So if for one parameter we find the optimal value of the other, then for smaller values of first parameter, only smaller values of the second parameter should be considered. And we can implement this divide and conquer style. Yeah. I guess one more very short comparison is this. Let's say there is a video game where you get experience and gold. Get experience, and because of that levels, and gold. And you are into speedrunning. You want to speedrun to get X gold for some value of X. Most likely optimal strategy is to first get some experience and levels to be stronger, and then just maximize your gold. But I claim this. Bigger X target suggests that bigger level target. In such a video game, you might wonder, should I get level 10 and then focus on getting gold from now on because I'm so strong and I will kill monsters very fast? But if you want way more gold, it makes sense to invest more time first to get some more experience and levels to be even stronger. Now, if you just want to get this amount of gold, there may be some linear solution. But what if the task says, for every amount of gold from 0 to X, compute minimum amount of time to do it. And maybe to know And maybe it's easy to compute if you know what is your target level. You know how much time it takes you to get level 1, level 2, and so on. And depending on level, you know how much you will spend on getting gold. If it's true that this, then we can apply divide and conquer optimization. Which means that we can try for middle gold or sometimes middle level, but we can investigate, I wonder what if my target is this. I will consider all possible target levels. For each of them I will compute the answer, the amount of time, and I will realize, oh, for this amount of gold it's optimal to get level 13 and then get gold fast. If you know this, then to get less gold, you will only investigate levels from 0 to 13. To get more gold, only levels from 13 up. And if it's similar kind of iteration as with our problem or in Meteors, I guess Meteors was different, then again, amortized time complexity will happen, and you will not have quadratic for every level and for every target gold you consider it, but instead you will have what you will have, I'm guessing gold plus levels times logarithm of something. I'm not going to now think logarithm of what. In our problem it was log squared because we also used a data structure, segment tree or a set. So this is behind this divide and conquer optimization. Any questions? So you have some links if you want to practice. There you are. In announcements, so what's next? Well, you can solve links. You can read links, read articles, solve problems like Meteors. You can upsolve problems from today and yesterday. Upsolve. Tomorrow is day off, but you already will be given a Polish Olympiad contest where if you prefer to do it tomorrow, that's it. Tuesday, 4 p.m. Polish time, is analysis of Polish Olympiad 2023 day 1. Or is it? Yeah, 2023. Which you will get access to tomorrow, and you can participate anytime between Monday and Tuesday, both days. If you have some questions, requests, put that in the server. I welcome any ideas for lectures. So far, though, I'm just giving lectures on some follow-ups on a problem that happened in the problem set, which is some, I think, reasonable approach. All right, thank you everybody for attending. Good luck with upsolving. See you on Monday. Bye-bye.